Dear students, welcome. Today we will discuss Diffie-Hellman Key Exchange. Okay. Diffie-Hellman Key Exchange, it is called as DHKE. Basically, it is a cryptographic protocol. It is used to securely exchange cryptographic keys between two parties. As you all know that in cryptography, one of the important aspect is the generation of keys. So if you want to perform encryption and decryption, we need to have keys. Input to the encryption algorithm is one is plain text and another one is we need to operate it with some key K. So then you transform a ciphertext called CT. Then again at the decryption end, input to the decryption algorithm is one is ciphertext and another one is the key in order to get the plain text back. So basically, this Diffie-Hellman key exchange protocol, it is used to securely exchange cryptographic keys between two parties. Okay, it is used to establish a shared secret. Dear students, this is very important. So it is used to establish a shared secret key between two parties without needing to exchange the key itself over an insecure communication channel. So basically, whenever we transform any messages or keys, usually we transfer it through an internet. Basically, it's an insecure communication channel. This is the place where Diffie-Hellman key exchange protocol come into play. So basically, it establishes the shared secret key between two parties without needing to exchange the key itself over an insecure communication channel. It is often used in conjunction with cryptographic algorithms like symmetric encryption, which is also called as private key encryption, and digital signature to secure communications. For example, once the two parties, say for example, Alice and Bob, have established a shared secret key using Diffie-Hellman key exchange, then they can use this key with symmetric encryption algorithm such as AES advanced encryption standard to encrypt and decrypt their messages securely. So basically we are using Diffie-Hellman key exchange to perform an operation in order to find out a shared secret key which will be used by sender and receiver. So the same shared secret key is used to encrypt and decrypt the messages. Let us see how to deduce the common shared secret key. Consider two parties, A and B, that need to agree upon a shared secret for the duration of their current session. So there is a session established. During that session, A and B wants to communicate to each other. For that, we need to have a common shared secret key. Okay. Assume that both A and B know the base G. Okay. So you need to make certain assumptions over here. Both A and B know the base G and modulus P in advance. Okay. Sender A and receiver B, you can call, or else you can call Alice and Bob as sender and receiver respectively. They both know the base G and the modulus P in advance. Okay. Then they participate in the following sequence of steps as below. So the main agenda of Diffie-Hellman key exchange or main intention in Diffie-Hellman key exchange is that you need to deduce the common shared secret key. Okay, let us see how to do it. Okay, so sender A and receiver B. So first, sender has to choose A. You can call it as a random integer. So the value of A should be greater than 1 and it should be less than P minus 1. Okay. So you need to choose A. Once you choose A, then you need to compute G raised to A mod P. Okay. So base is G. G raised to A, the chosen random number by A, which is what? Small a. G raised to A mod P. Okay. Now you send G raised to A mod P value to receiver, which is called as what? B. So the value of G raised to A mod P, it is called as what? Partial key. Okay, it is called as what? Partial key. Similarly, on the same lines, B will choose its own random number small b. After that, it has to compute G raised to B mod P. Okay, so both sender and receiver have to calculate this computation, that is G raised to A mod P at the sending end and G raised to B mod P at the receiving end. Now, the value of G raised to B mod P, which is also called as the partial key, which is sent to what? Sender A. Okay. Now, what receiver does is, so receiver is B. B has received the partial key G raised to A mod P from A. So again, what you need to do is, what receiver has to do is compute G raised to A mod P, that is the partial key received from A, and it has to be operated with B's random integer. So you perform an operation G raised to A mod P raised to B. So you can rewrite it as G raised to A into B mod P. So similarly, what A will do is, so A has received G raised to B mod P partial key, okay, from B. So again, A has to calculate G raised to B mod P raised to random integer chosen by A is small a. So therefore, G raised to B mod P raised to A. So you can rewrite it as G raised to AB mod P. So dear students, please observe here. So A has calculated the value, that is G raised to A into B mod P. Similarly, B has also calculated G raised to A into B mod P. Okay. So the common secret between A and B is therefore G raised to A into B mod P. This is the common secret. Okay. See, in the insecure channel, we are just transforming the partial keys, that is G raised to A mod P and G raised to B mod P. But we are not sending the actual shared key, okay, actual common secret. So actual common secret will be calculated at the sender end, similarly at the receiver end. Therefore, the common secret deduced is G raised to A into B mod P. Okay. The same steps, let us revise. So step 1, A chooses a random integer small a such that A is greater than 1 and A is less than P minus 1. Computes the partial key, that is G raised to A mod P, and send this to B. Step 2. Similarly, B chooses a random integer B such that B is greater than 1 and less than P minus 1 and computes the partial key G raised to B mod P and send this to what? A. Okay. Step 3. On recipient of A's message, B, which is nothing but a receiver, B computes G raised to A mod P raised to B mod P, which is written as G into AB mod P. Okay, by the rules of an exponential. Again, in step 4, on the recipient of B's message, A computes G raised to B mod P raised to A mod P, which is nothing but G raised to A into B mod P. Now you can see both A and B share a common secret, that is G raised to A into B mod P. This is the simplest procedure of Diffie-Hellman key exchange. I think you have understood. Let us solve a couple of examples based on Diffie-Hellman key exchange in order to deduce a common secret. Okay. Let us go through the problem statement. So P equal to 11. P is nothing but the modulus value and base value G equal to 2. Okay. And random numbers chosen by A, which is nothing but sender, and B, which is nothing but receiver, respectively 3 and 6. Okay. Deduce the common secret. What is the given value? Given value is modulus value P is given, P equal to 11, and generator or the base, you can call it base value is given, that is 2, and random numbers chosen by A is 3, random number chosen by B receiver is 6. Let us go through the algorithm. So according to the algorithm, A has chosen its random number, that is 3. Okay. Then A has to compute G raised to A mod P, which is nothing but 2 raised to 3 mod P. P is nothing but 11. 2 raised to 3 mod 11 is 8 mod 11. Obviously, it is answer is 8. Now this 8 is called as what? Partial key that is being calculated by what? A. Now this partial key will be sent to receiver B. Similarly, B has chosen its own random integer 6. Similar kind of computation has to be calculated over here. Compute G raised to B mod P. What is G? G is 2. What is the B value? B value is 6. 2 raised to 6 mod 11. Okay. 2 raised to 6 is 64. 64 mod 11. So what you need to do is you need to divide 64 by 11 and take out the remainder. 11 5s are 55 and the remainder is 9. So now 9 is called as the partial key computed by B. Now this partial key value 9 will be sent to what? The sender. That is the value of G raised to B mod P, which is nothing but 9, is sent to A. Okay. Upon recipient of this partial key, so partial key is G raised to B mod P. G raised to B mod P raised to A has to apply its own random integer, that is 3. Okay. G raised to B mod P raised to A, which can be rewritten as G equal to G raised to A into B mod P. Okay. G raised to B mod P value we already know, which is nothing but 9. Raised to A is nothing but 3. Okay. 9 raised to 3 mod 11. 9 raised to 3, if you do it, the value comes around 729. 729 mod 11 value turns out to be 3. Okay. Similarly, P has to compute upon receiving G raised to A mod P. What B has to do? G raised to A mod P raised to B. Okay. G, that is nothing but G raised to A into B mod P. What is G? G is G raised to AB, G raised to A mod P raised to B. G raised to A mod P answer is what? 8. Therefore, 8 raised to random number chosen by B is 6. 8 raised to 6 mod 11. 8 raised to 6 mod 11. 8 raised to 6 is nothing but 262114. If you do that, okay, if you do it with mod 11, so again answer will come out around 9, answer as 3. Here you can see that common secret calculated by A and common secret calculated B are same. So therefore the common secret G raised to AB mod P is nothing but the value 3. Therefore common secret is 3. This common secret can be used by A and B for the current session. This is about example number 1. Let us go to example number 2. Okay. In example number 2, what is the given value? Let P, which is nothing but the modulus value, P equal to 23 and G equal to 9. G is nothing but the base. G is nothing but the base, and the random number chosen by A and B be respectively 4 and 3. Okay. Deduce the common secret. Again, the same procedure. You have A, G raised to A mod P. You do it. What is G? It is 9. 9 raised to 4 mod 23. Answer comes around 6561 mod 23. In the previous video, I have told you how to calculate the mod value in the calculator. Simple calculator. First divide 6561 divided by 23. So answer comes around 285.26. Take out only the decimal integer that is 285. So 285 has to be multiplied with the modulus value, which is nothing but the 23. So answer comes around 6555. It has to be subtracted with the number 6561. 6561 minus 6555. So answer is what? 6. What is the meaning? The partial key computed by A is 6. Okay. Similarly, B has to calculate its own partial key by the formula G raised to B mod P, that is nothing but 9 raised to 3 mod 23. Okay. 729 mod 23. 729 by 23 is 31.69. So answer is 31.69. You take out only the decimal part. 31 into 23. Answer comes around 730. It has to be subtracted with the number 729. So the result is 16. What is the meaning? Partial key computed by B is 16. Now, B will share its partial key with A, and similarly, A will share its partial key with what? B. Okay. B having received partial key generated by A, which is nothing but 6. Okay. And it has to apply its own random integer, which is nothing but B, that is 6 raised to 3 mod 23. So if you do 6 raised to 3 mod 23, answer comes around 9, value 9. Okay. Similarly, A, upon receiving partial key, that is G raised to B mod P, which is nothing but 16. Okay. 16 raised to 4 mod 23. If you do it, so the answer comes around 9. So therefore, the common secret shared between A and B is what? 9. Okay. The simple example, just you need to properly calculate the value of the modulus. Okay. I think, hope you have understood it. So let us go through one more example. Let P equal to 131 and base G equal to what? 2. Let the random number chosen by A be 24. So her partial key is G raised to A mod P, which is nothing but 2 raised to A, that is 24 mod 131, which comes around 46. This is the partial key. Similarly, let the random number chosen by B be 17. So his partial key is 2 raised to 17 mod 131, which is congruent to 72. Okay. After receiving B's partial key, okay, which is nothing but 72, A computes the shared secret as 72 raised to 24 mod 131, which is equal to 13. Similarly, after receiving A's partial key, B computes the shared secret as, that is 46 raised to 17 mod 131. If you do it, answer would be 13. Both matches. So therefore, common shared secret is 13. So this common shared secret is used by A and B for further communication for the entire session. Yes, thank you.